see. Today I'll be like to present our work for like singulating object in packing environments using Dexterous. So we specifically focus on like the object singulation problem, where we have a target in a cluster. Our goal is to first isolate the target and then grasp and finally retrieve it. So this has a bunch of applications. The first one, if we were to like separate a certain layers of fabric from a stack of them, like in this previous work, we need this kind of scale. In addition, like suppose we're trying to like extract an item from a cluster, like a book on a bookshelf, and this is also useful. For example, in this related work, they're trying to singulate the top ball from a stack of balls. However, this task is pretty challenging because first of all, like it has a cohesion issue because we have these non-relevant objects that may block the target ball. Also, like since we are manipulating a cluster, this requires like a high precision to just get the right target from like these clusters. So for our problem, we focus on like a packing environment, which is like a bookshelf like this. So many of the previous methods, they use technique like push and then retrieve, where they sort of like push the target block. I mean, in this related work, they're trying to push like they're trying to singulate the red block, but they use like a push and then retrieve method to like gradually do the singulation. But in the bookshelf case, we can't do that. Also, as like I record a video on my phone, like I'm trying to like singulate this book from the box. So in this case, I can't just naively push the other like neighbors and then retrieve it. I need to somehow like create space in between the target block with its neighbors, and then at the same time, I then like take my hands in and then do the grasping. So for this kind of task, as shown in this video, I'm using my hand to do the task. So intuitively, like getting intuition from this, we propose, just like human, to use a high degree different Dexterous for object singulations. Specifically, we use the Libra hand, which has like 16 degrees of freedom. And we discovered that like policy tries to use like some of our fingers to stabilize the target block, where we use other finger as actors to like push aside its neighbors to create space for our hands to go in. And there's also some related works that's trying to like have this similar pattern, like in this one, in like Cora, where they're trying to like use one hand as stabilizer and then a hand as actor to like twist this box. However, they're using like a bimanual system, but for our task, it's more like a single hand manipulation for object simulation. Yeah, so actually like Dexterous manipulation it has a lot of works. So the famous one is like OpenAI's in-hand reorientation, like the one they reorienting like the Rubik's Cube. And we also have like a bunch of in-hand rotation, hand spinning, and etc. So our work is considered as like one member of like a group of work like this. Yeah, so this is like a brief demo of our work that we try to singulate and grasp. So it can generalize to different number of blocks, different level of tightness, and etc. Yeah, so let's just briefly go review like the overall pipeline, which is like we use reinforcement learning with PBO to train a policy, and then we like basically design a report based on like extracting the target block from the cluster. And at the end, we perform zero-shot synchro transfer using ISRR NVIDIA simulator. And finally, we're able to isolate, grasp, and finally retrieve the target block. So to be more detailed, the policy needs to like perceive the current hand configuration to know like what my hand is, and it also needs to know where's the wrist. So it also taking like the end effective position. And in addition, like the most critical observation perception for our policy is it needs to like perceive like how my target block is compared to its neighbor. So we use this block corner vector to represent this. Also, we're using like a multi-phase training pipeline, so we have a phase indicator to tell the policy which phase am I in, so you can output the action correspondingly. So as shown in the pipeline, we start our hand on top, and then we like lower it up to isolate, then grasp, and finally retrieve the target block. So first talk about the like block corner vector as the representation. And I think this representation is the abstraction of the task that we basically capture the essence of the task, because we are trying to like separate a target from the neighbor, and the simplest way to represent like a block is to use like k-point on the edge, so as a representation, and then like we have this displaced vector that points to the neighbor. So intuitively, the magnitude of such vector just represents like how successful our like isolation task is. Also, like this kind of representation is like invariant to like different settings. So we can use the same policy to singulate the left, the middle, the right, or just any block. Because like for the cases of the left block, we can just consider the neighbor as like the wall of the box, etc. Also, like this can bridge into ROGAP because it's an abstraction of like a state like image. Compared to that directly fitting image to our training, this one has more like training efficiency. So also we employ like a multi-phase training pipeline where we proceed through like each training phase sequentially. Sorry. Each phase has like a end effector height and like specific reward design to encourage specific behavior for each phase. So I'll start a hand there and then a reward design trying to isolate the target block. And then we move like the end effector down for like grasping and then lift it up for retrieving. So I'll go through this in more detail in the next few slides. During the isolation phase, of course I need to like avoid lifting other like non-relevant blocks because we need to singulate. And also I need to like maximize such displacement vector, which is pretty intuitive. As shown in this video, like the hand is keep trying to like maximize the target block from its neighbor, but like because the reward design is trying to encourage such maximization. And the hand just keep doing that until it will like lower down the end effector, and we will also encourage like a minimized distance between each fingertips and the block surface to like encourage a strong grasp. Also, like the reward design encourages at least 2 contact points to form a force closure so that I can firmly grasp the block and then lift it up. In the last stage, which is the retrieving phase, we're trying to like just lift end effector up and maximize the height reward so that the policy has a strong bonus in the end if it's successful. But because I'm training everything like in a row, it also have like the encouragement for the previous phase to like have a firmer grasp so that it can like have more success probability for this stage. Like after I train them in a row, the last step is like I have a policy in simulation, but I want it in the real world. I want like a real world process that can do this task. So I do like synchro transfer from Isaac Gene to the real world. So common technique including like the linearization. For example, I randomize like the neighbor block spacing so that it can generalize to different level of tightness. And also randomize other terms like hand initial position and other physical property, oscillation space, acting space, etc. In addition, like our state representation is an abstraction or a task which intuitively just can be like easy for synchro transfer because it's all K-point based. And we also do like system identification, like tuning parameters for our controller. And also our common techniques for like Dexterous manipulation, like we use a smoothing factor to make our hands motion more smooth. Otherwise, to like prevent jittering effects. So let's go into our results. So after we have a policy that can work in real world, we try to run a policy in different environmental setup. Like we have like 3 blocks, 4 blocks, and also like in different level of like packing densities. So on the right one is the most packed, and the left one is the least. And we figure out that like since our serialization data is invariant to this like kind of like difference, we're able to just zero-shot the product policy. Also, like the randomization, as mentioned in the previous slides, enables such robustness. And our policy is able to generalize to like different kind of environments like this. But in addition, like I try to do something interesting. Like I'm trying to like during the isolation phase, I'm trying to manually decrease such displace factor and see like how the policy reacts. So it's trying to like still like holding the target block and taking control of it and prevents it from like me. So it's trying to keep it singulated, and so that eventually it will like just move down and grasp. So it shows that the policy is able to like handle like disturbance from external factor like me. So we also compare policy with like non-linear baseline, where like we use like the method to like the naive one, like we try to push aside neighbors and then retrieve. But in this case, it's like too compact. If it pushes aside, it comes back. So like naive method can't do this, but our policy can just continuously like create space and eventually take opportunity and then goes down. So as shown in the comparison here. So we also show some numerical results. So it basically tells us that well, a constrained environment is definitely more challenging the baseline, like the non-linear baseline, like push and then retrieve, can't handle the constrained environment, but our policy has a comparable result that's shown in like the success rates. Well, we also learned that like better simulation result does not imply better real world result, because the positive qualities in real world is not the best in simulation, but it's the one that works best in real world. And lastly, we release all the experiments videos. So every number in this table corresponds to a YouTube link in our website. So we like just open source everything for like peer-to-peer. Yeah, and also that's the lesson learned during doing experiments I like to share. So during experimental pipeline, we just put everything like in a spreadsheet or in other anyways that's organized. But we also use like a clapperboard system. Like in the movie, we have a count and action. So this helps us remember like what we did, so as shown in this image. So if we rename the like video wrongly, we can check it to see okay which trial am I in. So I think this kind of methods, although it's kind of tedious, but if you get used to it and integrate it into your pipeline, it could be like increase your efficiency eventually, and it could also encourage like community to like see more open source like full videos of every experimental trials. And we also encountered failure cases, of course. So we categorize it into like two types. So the first one is like isolation failure, where policy just failed to do isolation. Another one is like after I do isolation and I grasp, it's not firm enough, so as a lift, they can't like grasp the target. So those are the two type of failure cases that we summarized. That's common in like all the failure trainers. So in conclusion, we use our vector-based like design and the like multi-phase training pipeline, which enables like using high degree of algorithms to do the simulation, and also show that simple is possible for such context-rich tasks. However, like I think our work has also like a lot of limitations. First, as shown in this image, like for the real-world perceptions, I require protect markers to like have like real-time detections of the edges to like bridge a simple gap. And in addition, like in our pipeline, we treat each block equally, which is not realistic in the real world, because like in real world we have like you can kind of book different like schematics, like maybe some are fragile, maybe some are like easy to deform, etc. Also, like for occlusion, we have like two camera mounted to capture the vapor tag, but that's also like I would say like an engineer setup for like occlusion. And as I said again, like our presentation is good for rigid body, but consider deformable objects, yeah. So that's like the limitations of our work. So yeah, thanks everyone. And also like thanks all the collaborators, Yuhai, Hanyang, and Daniel. Yeah.
Question, please. Costas.
Thanks, very nice work. Very big supporter of the idea of videos for experiments. Good message. And the gating of the fingers was really interesting to see. But something I don't like, reward engineering in RL, with dense rewards, because I'm worried how much you may be able now to generalize to different settings. It would be nice if perhaps you had just a sparse reward and then you could learn and perhaps come up with these strategies. What do you think?
Mm-hmm. Yeah, I think I agree with your points. Like reward engineering like is first of all tedious, of course, and I think like for improvement of our current work, like we need like a better perception module that can like sort of like first get rid of like the vapor tag, and then like we can like prepare like all the priors, like prior perception module that we know like where to singulate and etc. And then like we just derive a policy then. But yeah, I agree with your point. I think a stronger prior can like bootstrap the entire pipeline a lot compared to just doing reward engineering like our yeah.
Thank you.
So we have two questions or three. And our next speaker, please come over and then make your connection now.
So what do you think limited your performance more, hardware or software?
Yeah, I agree with your point. I think it's hardware because, well, the liver hand is bigger than human hand. So as I'm doing the demo, like in my home, I can easily do the simulation. But for a liver hand, it's bigger and it's pretty rigid. Like human hands are deformable because so that they can be like more flexible, like it has impedance, etc. But a liver hand is purely rigid. So even though like our work is on the software side, but I think the limitation comes from the hardware side. I also agree with like the talk yesterday that I think the constraint comes from the hand design. there's other work, I think they're trying to use like soft hand to do the manipulation, which I think also like if you could have like a deformable in the factor, that would be like pretty exciting compared to just relying on the hardware and like just tune the word and equals exact rate. I think yeah, consider my future role. I like to explore more on that. Yeah.
We can take one more question, John, please.
Can you hear me?
Mm-hmm.
I don't think you've made the case for a multi-fingered hand for this task. From what I can tell, you could just use 2 fingers. I bet you could do this with a vice gripper. And so, from what I can tell, this research could take 1 of 2 directions. The theory of manipulation, which could include a vice gripper, or if you want to use a multi-fingered hand, I think you need a more complex task.
Yeah, I agree with your point. Like, I think in terms of like if we have the flexibility to like use all kind of like hardware design specifically for our task, I think the easiest solution is a suction gripper and like attached to the target block and then the chip, right? But another motivation of work is to I'll take it here. Is to like fully explore the dexterity of like a Dexterous hand. I think this bridges into like 2 directions. The first one is we have a universal manipulator and trying to like adapt to different tasks. Like in our case, we are in this category where we treat the hand as a universal manufacturer and to see if it could work for a simulation. And because later on we may use it for other like manipulation tasks. Another like route is like we can have a like deformable indifactor that can like a soft robot that can like change shape based on like different tasks. And I think that would be like much more exciting.
Just real quick, I just want to add, I think it is really now up to John to prove that it's going to be done with a vice grip. A vice grip is a very odd choice. I don't think it can be done with a vice grip. I think it's a really great task. It's actually a really interesting one that humans do all the time. I think you did some really nice work on this, and I think it may not generalize, but it's a really interesting step in something that we do all the time, and I haven't seen anyone actually address this problem before, so I salute you for your choice of problem.
Yeah, thank you.
So I think John, we have a question, right? Let's finish it off.
Yeah, it's still on the line of generalization. This task is a very specific one. What lessons do you take for another thing? Like if the shells is on the wall, if what can you really bring out of this?
Yeah, I think what I can bring out is like I think this is specific to the setup that we have, but like in order to like really have a dexterous hand in the real world to retrieve a book from a bookshelf, we still need a long way to take. So for example, like even if I just flip the bookshelf, because like when we retrieve book is like in different gravity, like gravity affects a lot. Also for like controlling, also for like the policy itself. So like we have to handle like all these complex variants in real world, but in simulation we have limited ability to model them. So that's like the lesson learned for like the limitation in simulation or like simple rule pipeline.
Excellent. Let's thank our speaker again.